Hey everyone, thanks for joining. We're going to be talking about microcontroller security in Meta's first generation of smart glasses. Firstly, let's introduce ourselves. I'm Octav. I'm a security engineer working for Meta in London, currently tackling the security of Messenger app, and I'm also a cryptography enthusiast.
Hi, Magal. I am also a security engineer at Meta. I focus on Reality Labs products, so glasses, headsets, everything physical. I love embedded stuff and everything low level.
Let's quickly go to the agenda for today. We're going to start by giving you more details about the device we've exploited, following the motivation of doing so. Then we're going to show our exploit setup and the challenges that we had to overcome. Lastly, we're going to talk about the mitigations that were implemented as a result of the exercise. Reality Labs is a division at Meta that builds these new products such as the Meta Quest or the smart glasses. The goal of these devices is to provide new experiences as well as to improve collaboration. You should definitely check one of these devices if you haven't tried them out. They're really cool. Now, talking about smart glasses, Meta launched 2 generations in partnership with Ray-Ban. The first generation provided a camera that could record audio and video in a pair of sunglasses. The second generation brings live streaming straight from the glasses as well as a smart AI assistant. At Meta, besides our automatic vulnerability discovery work, we regularly perform manual security code reviews. Sometimes we find really cool bugs that we think could be worth a full working exploit. So we plan for an exploit exercise, which internally we call defense through offense. The end goal of this exercise is to harden our products by implementing mitigation and prevention mechanisms that would kill our exploit and ideally make every step of it unusable. We have a really cool blog post about the defense to offense exercise that we did on the Meta Quest 2 on our engineering blog. Now, for some background about the vulnerability, a security code review that we did on the BLE stack of the first generation of the smart glasses issued a very interesting zero-click memory corruption vulnerability. The odd thing, however, was that the vulnerability was on real-time operating system, which is none of the usual Linux or Windows kernels that we are used to. So we asked ourselves, how would we exploit this? Since this seems like a very good candidate for defense through offense, and there was a lot for us to learn here, we created a plan and executed the exercise. Before jumping into the actual vulnerability, let's chat a bit about the high-level architecture of the smart glasses. The device is formed of 2 main components. On top, a powerful SoC used for running the more demanding services, and on the bottom, a smaller microcontroller, which is running FreeRTOS, used for more power-efficient operations. The device can talk with the companion app via Wi-Fi for things such as file transfers and via Bluetooth. We call this proximity attack surface. On the Bluetooth side, we see that the MCU is responsible for handling the received data, which is going to be important very soon. The glasses are using BLE, which stands for Bluetooth Low Energy, for communicating with the companion app. In contrast to the usual Bluetooth technology, BLE is far more power efficient, which makes it great for a small battery device such as a pair of smart glasses. On BLE, developers can expose services and characteristics for which they can define properties. These will give us 0 or 1-click proximity attack surface based on whether pairing is required for these characteristics. A read-only characteristic would be used, for example, by a temperature sensor from which we need to just read the temperature, while in our case, we were facing a read-write characteristic because the companion app should also be able to write onto this characteristic on the glasses. All right, let's jump into the actual vulnerability. The bug itself was discovered internally and then patched in early 2022. An attacker in BLE proximity, which according to Wikipedia is around 100 meters, pretty generous, could send a specially crafted packet over an exposed characteristic. The first handler of this data is some code running on an RFIC chip, which will then forward the data to the wireless module running on the MCU. On the MCU module, we found a stack buffer overflow, which eventually allowed us to execute our own shellcode, as you will see. Keep in mind that at the time of the exercise, the MCU didn't have any DEP or canaries protections. Also, ASLR is not really common for microcontrollers of this size, so that was an issue. That wasn't an issue for us as well. In the code running on the RFIC chip, a unique ID is used to define a BLE characteristic that you see on the top, and then this macro is used for registering it. Two key aspects are to be noted here. The characteristic is marked as writable, meaning that it can receive data, and secondly, there is no pairing needed for this, meaning that this is part of the zero-click attack surface. Now, in the first-party code running on the RFIC chip, we handle BLE write requests in a switch case. And then, using a statically defined buffer of 512 bytes, we are copying the received data to be forwarded. Lastly, the frame, once it's forwarded to the MCU, where it will be handled by the RxFrame event loop function. This function is copying the frame into a local stack buffer. However, as you might have noticed, the frame length can be at most 512 bytes, and the local stack buffer is only 128 bytes, which means that we have a 384 bytes stack buffer overflow. Let's quickly talk about the setup. With this vulnerability in mind, the first goal for us was to trigger it and hopefully get a crash of the MCU. Initially, we tried to use our phone for sending data over BLE, but since our laptops can do that as well, we ended up using the Beak library in a Python script. The script discovers nearby BLE devices and then filters them one by one. We are looking by the BLE name, which is a predictable name for the smart glasses, and then we can enumerate all the BLE characteristics. Remember the unique ID from earlier? We can use that to find the characteristic we are interested in, and then finally we can write raw data payload to it. Now, a quick word about debugging. The challenge was that since this is a real-time OS, we weren't able to attach an interactive debugger onto the target. However, we have MCU logs available over ADB, crash dumps that are produced when the MCU crashes, and lastly, we have the source code so we could flash the device with a custom firmware. We did add some helpers onto the firmware to assist with memory inspection. Although this exploit was 100% doable, without this, we just made our lives easier. Now, back to the vuln. We know we can send 512 bytes, and these bytes are not exactly random. In reality, we need to send a null byte, followed by the length of the payload, and then for the actual data. So sending 512 A's and then checking the logs, we see that the MCU crashes on a dictated hard fault, which means that we successfully were hitting our vuln at this point.
So let's discuss the exploit process. Now, I know what you think. In first glance, we have 384 byte buffer overflow on a system with no stack canaries, with no ASLR, no memory protection. Seems simple enough. Put the shellcode on the stack, overrun the return address, and have a nice early 90s exploit. But it ended up being a little bit more complicated than that. So first reason why not is that the function where we had the vuln was a worker function that just, all it did was receive BLE messages, process them, then go to sleep. The problem was that it never returned. It's an endless loop. So we can override the return address, but nothing comes out of it. So we were getting a crash. So looking at the crash dumps, we saw that the crash was due to an assertion due to a stack overflow. Now, first of all, that was a surprise because we didn't expect to have any exploit mitigations whatsoever. So what was this about? And when looking at the FreeRTOS code, we found out that there's a stack overflow mechanism. Basically, FreeRTOS puts a canary at the end of each stack, and when a context switch happens, it checks that the stack is still there, the canary is still there. It's a constant A5, A5, A5. And we assume it was meant for stability and not security, otherwise the constant canary is a bit weird. But yeah, so we realized we need to understand why we were triggering that, and in general that we need to understand FreeRTOS a little bit better in order to complete the exercise. So for those of you less familiar, a quick primer. FreeRTOS is possibly the most common real-time OS in the world. Don't take my word on it, but I think it's the most common one. It's open source. It supports so many families of MCUs and architectures. And it has no MMU support because the target hardware just doesn't have an MMU. So what you get is one flat monolithic address space where you have all the kernel and all the tasks. And when I say task here, so tasks are just a thin layer of abstraction on top of a thread. So you have a one-to-one between threads and tasks. Now, the way FreeRTOS manages tasks is through something called a TCB, task control block, which is a big struct that has everything that the kernel needs to know about the task, like the name, the priority, the state, the location of the stack. And the way it manages tasks in general is that the TCBs are linked in doubly linked lists. So you would have something like a doubly linked list of all the tasks in the system that are in the ready state, meaning they are ready to get execution time, and another list for all the tasks that are in the blocked state, and so on, somewhat like a task struct in the Linux kernel. And in terms of memory layout, when tasks get created, then FreeRTOS would allocate a stack for the task, and then a TCB, and then a stack, and then a TCB, and you get this pattern of stack TCB, stack TCB, stack TCB. And what happens when you overflow a stack, then you would reach the TCB of the task that you were targeting. That was what our overflow was doing. We were overwriting our own TCB, which looks like fun, right? Because a TCB looks like a very juicy target to look for corruption candidates in. There was nothing obvious like function pointers, but there was the next best thing, which is the node of the linked list. If you remember, those things are linked in linked list. The first thing we thought about doing was to use an unlink primitive, basically wait for the kernel to move this task to a different task, and at which an unlink will happen, and we could have a write primitive due to the unlink, but that was not very stable. So we decided to look for another approach, and then it hit us that we are trying to get control of the execution flow. And the TCB is in essence a mechanism for managing execution flow, controlling what gets executed when. So instead of going around and doing more memory corruption, we thought, why not use the TCB for what it was meant for, and basically inject a TCB of our own and inject a task into the FreeRTOS system and get that executed, which sound more interesting. So the plan was to overwrite the next variable in our node, so that instead of pointing to whatever task it was pointing to, it would point to some TCB that we inject into the memory. And the nice thing is, because our task was in the list of tasks that are ready to be executed, whatever is pointed by this next variable is indeed going to be the next thing that will get executed on a context switch. So looking at what would happen at a context switch is pretty straightforward. When a task is preempted or it yields, and when it stops execution, then we get the execution context dumped to the stack, and a pointer to that context is stored on the TCB. And the next time it gets execution context, then it will just resume execution from there. So we built a chain that looks something like this. We use the vulnerability, we send a message, we overflow the next, we point it to a fake node, which is part of a fake TCB that we place somewhere in memory, where the fake execution context is a fake execution context that we also put somewhere in memory, that when it gets executed, it will execute a shellcode of our choosing. So as you can see, there are several artifacts here. There's also the question of where we place them in memory. One thing we could do is cram them all inside the overflow. And the other option is we actually had another primitive, another GAT BLE that was unlocked, and you could write 512 bytes to, and nothing would happen with those bytes, but we could just place them in memory, which was nice, so we could use that as well. So we built all of that. That snippet is the implementation of the TCB struct in Python from the exploit. And we hit send and waited for the glasses to crush. And we were getting Stack Overflow assertions again, which was weird. If you remember, we already had Stack Overflow assertions due to a canary that FreeRTOS was placing, and that was something else. And when we go back at the handler for context switch, we can see on top, you can see the loading of the popping of the registers from the stack with this LDMIA instruction. At the bottom, you have the branch instruction that branches to the stored instruction pointer. What we ignored was this MSR PSP-LIM. For those not familiar, so PSP-LIM is an interesting register that exists in the Cortex M33 that we were targeting. It's basically a mechanism for hardware detection, hardware-based detections of stack overflows. So when a thread starts executing, you put the bounds of how far the stack should go for that specific thread in this register, and if it does, you get a fault. But luckily, we controlled all of the context, so we could control that as well and place a register that would not stand in our way. Yep, so we did that. We hit send, and that worked. You will see a demo soon, sort of. We triggered the chain of event, which is sending the BLE message, overwriting the next variable, waiting for the task to stop because it has no work to do, so it yields. The next task gets chosen for execution. That's the task that we injected into the system, and the execution resumes from that context to execute our shellcode. So now we could start thinking about what to do with those shellcodes.
Now, we wanted to have a visual demo of our RCE, like something that even a non-technical person could understand. There are many juicy candidates that we could consider for this. Things such as silently triggering a photo or a video capture on the smart glasses, or even leaking broadcasted audio data. Remember that these glasses can be used to take audio and video calls, or they can also be used to read out WhatsApp messages, so there was some interesting data in there. However, our exploit is messing up with the TCP linked list, and it's basically leaving it in an unstable state, which means that on the next context switch, the MCU will crash. While it was completely doable for us to get the list into a stable state, we found an even quicker way. We made use of the flash memory that was existing on the glasses. So the glasses have a separate flash memory for storing persistent information, such as the BLE name, which obviously needs to be configurable. Flash memory has a different address space layout than the memory on the MCU, so we couldn't just use memcopy to write onto the flash memory. Instead, we needed to search for some gadgets. Luckily, we can reuse some functions that work, that can interact with the flash memory, namely the SPI flash, write, read, and erase methods. Bonus points, these methods are not doing any context switching, so it means that with our current exploit, we can definitely use these gadgets. Now, on flash, we can only operate on entire sectors. So we need to read the entire sector into which the BLE name will be saved. And then we change it in the MCU memory. Lastly, before writing it back onto the flash, the flash memory expects us to do an erase first. So we need to call erase and then finally write back the sector, hopefully save a persistent state onto it. Now, we developed our exploit on a debug version of the firmware, but the goal was to port it to a production image and show that it works on a production build. Since this would be a different build, it means that all our gadget offsets would be different. And in order to find these offsets, the usual flow would be to just take the OTA update package, reverse that, which was actually a pain given like how the firmware is compressed and saved inside the OTA. So we realized that we have a smarter way of doing that. We can leverage our own vulnerability to leak the offsets of the functions that are used to interact with the flash memory. For this, we made use of an assertion function that was part of some early code placed on a lower offset, which means that it was mostly consistent across production builds. So with the right format string, we could fail an assert and display an error message. Inside the message, we could display the addresses for the gadgets we were interested in, meaning that we could successfully leak them and then use them in our exploit. All right, so at this point, we had a working POC, and now it's time for a demo. For the actual demo, we went full movie mode, like trying to transmit the idea of what a real-life exploit scenario of a proximity attack would look like. So Magal in this video is going to be the victim. He's enjoying his smart glasses in a bar. He's taking pictures with them and then inspecting them on his mobile phone.
That's what I do.
Now, I'm going to be the attacker. I'm going to be sitting at a nearby table. Remember, BLE range can be up to 100 meters, so I don't, like, Magal doesn't have to see me. I can be hiding around the wall or something. The glasses are having a Bluetooth name called RB Stories 19, which is the expected, this expected default name of the glasses. I'm sitting in nearby range. I'm running the exploit, looking to compromise his glasses. Now, a few moments later, Magal notices that now his glasses are called hacked RB, which means that the exploit was successful and the glasses are now compromised. Let's talk about mitigations that resulted as part of this exercise.
Yeah, so besides having fun and making cute videos, our main goal was to improve the mitigations of our MCUs. And I noticed in this conference there's a recurring theme of firmware that has an attack surface but zero mitigations, like the USB-C controller on Macs, and someone mentioned the MediaTek on Samsung this morning that has no mitigations. So we were trying to think what we can do to level up our level of mitigations in this MCU and in MCUs in general. One thing that's very obvious is that it would have been nice to have memory protection of some sort. Now, the device, those MCUs don't have an MMU, but those ARM cores do have an MPU, which gives you a way to define regions in memory and provide specific access rights to each of them in a privileged or non-privileged mode. There's actually, FreeRTOS does provide you a built-in way to do that, where you isolate one task from another and one task from the kernel. The problem is that it's very hard to deploy unless you built your MCU from scratch aiming to use that, and it also has a performance cost, because every time you context switch, you need to reprogram the MPU registers, and you waste some 40 cycles on that, and that could be significant. And there's even a talk from Blackhead 2 years ago about why so few companies actually use this feature in MCUs. So to bypass that, we said, okay, so we don't deploy that, but it should be quite straightforward to just employ a static MPU layout that just takes all of the space that is going to get allocated for stacks and heaps and everything else that's not supposed to be executed, and place an NX bit on that, or to make the code immutable. So that's cheap. It has no cost in terms of performance, and that was easy to do. So we do that now when we adopted this as a policy in MCUs that have significant attack surface. The second thing is stack canaries that obviously would have been helpful. Now, there's really no reason not to have stack canaries in firmware. It's a compiler mitigation. There are just a few caveats to take into consideration. One is that you need an entropy source for the canaries. So in our case, we were working with an NXP chip that has a hardware-based RNG, so we could get entropy from there. The second is, if you remember, we are talking about a monolithic address space, and you apply a stack guard for all of that, so you need to be careful about when you do that. Otherwise, you might get a function caught in the middle while you replace the value of the stack guard, and the prologue will be different from the epilogue, and you mess things up, so you need to do it carefully. And lastly, once we were testing the stack canaries we implemented, we noticed something strange. First of all, we were checking the value of the guards, of the canaries we were getting, and they were surprisingly repetitive after boots, and they look suspiciously like an address from the address space of the image. And we looked into it, and it turns out that many versions of embedded GCC, older versions, have this funny bug where there's a missing dereference. So instead of placing the value of the stack guard, that's the random thing that you want to have as the canary, it was placing the address of the stack guard, which of course in a system without ASLR would be the same value all the time, and you can get that from reverse engineering quite easily. So that was nice. We weren't actually the first to notice that, so I linked a blog by a Christian writer that describes it in 2021. If you are using embedded devices and you want your canaries to work, make sure that you're not using any of the affected versions of GCC. And finally, we did a good job auditing the code, but don't take our word for that. We have a good bug bounty program, and it now covers all of our devices. For example, this one would have been a 45K for zero-click RCE, which is pretty nice. 30K for secure boot bypass, and a lot more for the apps, by the way, for Instagram, WhatsApp, whatnot. So, yep, that was the story about discovering the bug and learning how to make MCUs a bit safer with that. And a special mention to Andrew Calvano and Sapiti Panda that were instrumental and helped a lot on the exercise. Yep, thanks.
We are open to questions both now and offline later if you have some. All right. Oh, sorry. Go ahead.
Which microcontroller was this running on, if you can disclose that?
That was an NXP RT600 running ARM Cortex-M33, if I remember correctly.
Thank you.
How much of this research was assisted by internal documentation or code that maybe you wouldn't have access to as an external researcher?
A lot. Yeah, I mean, we are the vendor. We have the code. We found the code. We found the vulnerability reviewing code that we had. We could flash the device. It would have taken much longer to do it if we were not working for Meta, obviously.
Right.
All right. Thank you, everyone.